Back in 2008, a 9-page paper popped up online from someone called Satoshi Nakamoto. And this paper, it proposed a really elegant solution to a problem that had stumped computer scientists for decades. So today, we're going straight to the source. We're going to tear down that original white paper to really understand the why and the how behind a purely peer-to-peer version of electronic cash. All right, let's get into it.
First, let's frame the core problem, the big question at the heart of all this. With a physical dollar bill, it's easy, right? If you're holding it, it's yours. But digital stuff is a whole different ballgame. Any file, any piece of data can be copied perfectly, over and over, for basically no cost. So how on earth do you create a digital dollar that someone can't just copy and paste and spend 1,000,000 times? That's the huge hurdle any digital cash system has to clear. Now, to really appreciate Satoshi's solution, we first have to understand the world he was trying to replace. Before Bitcoin, pretty much all online commerce ran on what the paper calls the trust-based model. And this slide really lays out the big weaknesses of that old system. See, when you buy something online with a credit card, you're not actually paying the merchant directly. You're going through a trusted third party, like a bank. This means you need those big financial institutions, and that adds costs. But more importantly, those transactions can be reversed. A bank can step in, mediate a dispute, and just yank the payment back. This need for trust trickles down everywhere, making merchants wary of their own customers and forcing everyone to just accept a certain amount of fraud as a cost of doing business.
And that right there, that's the mission statement of the entire paper. The goal was to build a system that completely cuts out that trusted middleman and replaces it with something else: verifiable, mathematical, cryptographic proof. A system where any two people can send money directly to each other, no questions asked, just like handing over cash.
So how do you even begin to build a system like that? Well, the paper starts with the most fundamental piece of the puzzle, defining what a coin actually is in this new world. See, in this system, a coin isn't some files sitting on your computer. A coin is its own history. It's just a continuous chain of digital signatures. Every time an owner wants to transfer it, they digitally sign a hash. You can think of that like a unique digital fingerprint of the last transaction. And with each transfer, a new signed fingerprint gets added to the chain, creating this public, verifiable record of its entire life. Let's walk through a quick example. Let's say owner 0 wants to send their coin to owner 1. They create a transaction that says, I, owner 0, am giving this coin to owner 1. Then they use their secret private key to create a unique digital signature on that message, and that signature is undeniable proof that they, and only they, authorized this transfer. And this process just keeps on going. When owner 1 wants to send the coin to owner 2, they do the exact same thing, digitally signing it over. The cool part is that anyone, anywhere in the world, can look at this chain of signatures and mathematically verify every single transaction, all the way back to the very beginning, to confirm the valid chain of ownership. Okay, this is a great system for proving who owns what, but there's a giant gaping hole in it. What stops owner 1 from sending this coin to owner 2, and then immediately creating another conflicting transaction, sending the very same coin to owner 3? This is the famous double spending problem, and solving it without a central bank is the real genius of this paper. So to solve this, the network needs a way to agree on a single shared history of every transaction. It needs to know which payment came first. In a traditional bank, the bank just decides, but without one, you need a totally different approach. The paper's solution starts with this idea of a peer-to-peer timestamp server. The concept is pretty simple. The whole network gathers up a bunch of recent transactions into a list, or a block. It then creates a unique digital fingerprint, that hash we talked about, of that entire block. This hash is then broadcast to everyone, which basically timestamps it, proving that all those transactions existed at that specific moment in time. And here's the really clever part that makes it all secure. Each new block doesn't just contain its own hash. It also includes the hash of the block that came before it. This creates this interlocking chain of blocks, a blockchain. So if an attacker tried to change a transaction in an old block, they'd change that block's hash, but that would break the link to the next block, which would break the link to the next one, and so on. To cheat, you'd have to rebuild the entire chain from that point forward. So this chain gives us a secure history, but that just raises another question, right? In a network where everyone is equal, who gets to decide what the next block is? How do you prevent total chaos? Well, the answer is to replace trust with hard mathematical proof.
This is done through a mechanism called proof of work. To earn the right to add the next block to the chain, everybody on the network competes to solve a really difficult computational puzzle. It's kind of like a global lottery that burns real-world electricity and computer power. The key insight is that this puzzle is incredibly difficult to solve, but the answer, once found, is super easy for everyone else to check and verify. And that's what lets a decentralized network agree on one version of the truth.
So, here's the crucial takeaway. Proof of work creates a voting system where your vote is determined by how much computing power you have. The majority decision about which version of history is the right one, well, that's simply the longest chain. Why? Because the longest chain is the one that has the most proof of work, the most computational effort invested in it.
Now, this table from the paper shows just how mind-bendingly secure this whole system becomes. Let's say an attacker controls a pretty huge 30% of the entire network's computing power. If they want to reverse a transaction that's already buried under 5 new blocks, they still have about a 1 in 5 chance of succeeding. But just watch what happens as the honest chain gets longer. After 15 blocks, their chance plummets to just 1%. By 24 blocks, it's less than 0.1%. The security here isn't absolute, it's probabilistic, and it gets exponentially stronger with every single block that gets added.
So we have all the pieces, a chain of ownership, time-stamped blocks, and proof of work to lock it all down. But that leaves one big question. Why would anyone voluntarily contribute their computer and pay for electricity to do all this? What makes the whole engine run? Okay, so here's the network in action day to day. First, new payments are broadcast out to everybody. Then nodes, we usually call them miners, collect all these into a potential block and start that proof of work race. Eventually, one node finds a solution and broadcasts its winning block to everyone else. The other nodes quickly check it to make sure everything's legit, and if it is, they add it to their copy of the chain and immediately start working on the next block, building right on top of the one they just got. And this whole cycle repeats, on average, about every 10 minutes.
And this is why they do it. The node that successfully finds that block and wins the race gets rewarded with brand new coins, created out of thin air. That's the block reward. Plus, they get to collect any small transaction fees that people included with their payments. The paper makes this great analogy to gold miners. They spend resources, in this case electricity and computer time, to put new gold into circulation. And this quote just perfectly captures the economic elegance of the system's design. It brilliantly aligns everyone's self-interest with the health of the entire network. Think about it. Even a powerful, greedy attacker has a choice. They can use their computing power to try and attack the network, or they can use that exact same power to just play by the rules and earn the rewards. The system is designed so that being honest is simply the most profitable strategy in the long run. So let's just pull it all together. We start with digital signatures to prove ownership. We use a peer-to-peer network to publicly timestamp all the transactions into a chain of blocks. We use proof of work to make that history basically impossible to change. And finally, we use economic incentives to encourage people to contribute their power and keep the network secure. All those pieces together achieve that original goal.
This quote from the conclusion just nails the whole vibe of the system. It's not a company, it's not some organization, it's a protocol. It's a robust, beautifully simple network where all these independent computers, who don't need to know or trust each other at all, manage to reach a global agreement just by voting with their computing power. And that really leaves us with the big picture. This paper laid out a blueprint for peer-to-peer electronic cash, for sure. But the core invention, this idea of decentralized consensus, this blockchain, it's really a tool for creating a single, verifiable truth without needing a central authority. It's a foundational technology. And that leaves us with a final massive question to think about. What else can you build on a system that doesn't need to rely on trust?